Welcome to the viewers. We discuss today this idea of compact spaces, and for this let us consider topological space X tau is said to be a compact space if each open cover for X has a finite open subcover for X. That means here at first we are taking a topological spaces and we find this open cover, and each of these open cover that engulf these total spaces and which has the finite subcover and that also open cover. That means if you taking like this type of figure like X tau with the topological spaces, X is the space and topology is defined something, and if there are the many open cover that's also cover these spaces, and if we make some of the sheets that will cover this entire spaces suppose in it, and if these sheets that cover this total spaces, and if we shifting this sheet here and that totally cover the spaces X, and now if we say for this figure, and if we divided it, suppose the finite subcover like a rectangular shape, if this cover totally here X spaces X, and if there are the subcover all of these that also cover the spaces X, and there are countable in number like 4 here, suppose in many type of countable number of subcover that also cover this shape. This is our concept, and obviously this 4 will be the union of the subcover here, here that consists of only 4 subcover here we find, and if we say many subdivision they also made subcover, that's an arbitrary number, we don't know the exact figure. If we break another domain, another figure, here we get 1 2 3 4 5 6 7 5 6 7 9. That means 9 subcover is there also cover this type of shape, that is union of 9 subcover. So in this way we find the subcover. Idea of subcover, actually we making the approach of the union shape of the shape, and in the earlier cases, earlier video, what I defined, that's actually give some idea of covering simply, not I say about the union of this all cover, all subcover that makes these total spaces, but here I mention. And now this is a simply overall view and simple idea, and for the real number space R, with usual topology is not compact actually. Why these things happen? Because if we find all open interval, if open covers consisting all open intervals like this minus mm, where for m belongs to any integer number, and that does not have any finite subcover. If we say this type of covering that interval systems, and if we say the set of elements like m1 m2 mn in this way, then we can easily find as mm, and that can be also m1 m2 in this way, and if we say any number, let any number, say whatever may be the number, say L will be the length, suppose, and this is a concept of maximum or minimum. If we say m1 m2 in this way up to mk in this manner, then certainly we find in this type of region minus m1 this interval union of, that is, or compactly if we say, not to be right, just to write in this way, union of I is equal to 1 to up to k mi, and certainly this will be the region of minus L, because L is the maximum region, but which is fixed, and does not cover real number R. That is, finite subcover, that means subcover doesn't exist. If this is exist, that will also cover this interval. So we can say real number space R, the real number space is not compact. And we can say, for instance, every cases, in cases of real number, it is not compact, and every finite topological space is compact. We can say this for the compactness of the topological spaces, that every finite topological space is compact. We can say this result. And taking few types of example, that is because in a topological space, in finite topological spaces, what open covers, every open covers have finite subcover, finite open subcover, so it is compact. And many more examples of the compactness. Suppose the cofinite topology, if we say this any topological space x tau be any topological space and if x be the infinite set and tau is cofinite topology, then let, if we say cursive h be an open cover for X, and we fixed a member, that is h of alpha 0 of cursive h, then suddenly x minus cofinite topology, x minus h of alpha 0 is a finite set, and say that if we say like the element x1 x2 up to xm in X, since this cursive H is an open cover for X, the space, that is X can be written as union of this type of member, like this h of alpha 0, in such a way that alpha is arbitrary, so it belongs to arbitrary member of the index set like cup, we say, and there are members h of alpha 1, h of alpha 2 up to h of alpha m of cursive h, such that this if we say xi, that means this xi, and that belongs to h of alpha I for I runs from 1 to up to m, then h of alpha 1, h of alpha 2 up to h of alpha m with h of alpha 0 all forms a finite subfamily of cursive H, such that this X space will be given as h of alpha 1 union h of alpha 2 union up to union h of alpha m union h of alpha 0. In this way, that is, we find the subfamily. So x tau is compact, as we find the subfamily. It's also open cover and it finds in compact set. So in this way we get some of the idea about compact space in topological space. It is a compact space in topological space. We end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.